Next talk is massively parallel join algorithm.
Okay. Oh, sorry. Okay, there we go. Okay, hello everyone. I'm Xiao, a research fellow in science this fall semester, and later I will join Waterloo as assistant professor. I'm generally interested in designing algorithms for database queries from different aspects. For example, the scalability, low latency, learnability, obliviousness. And in today's talk, I will just cover some of my research on massively parallel join algorithms. And I hope you can find some interesting ideas from this talk. So the first question is, what is join? Join is a binary operator in relational algebra given two relations with some common attributes. It finds all pairs of tuples with the same value on the common attribute. So this is example of employee join department on the attribute department name. And when all tuples have the same join value, it just degenerates to a Cartesian product. When we have more relations involved, we can use the join operator together with some other operators such as selection, projection, or even aggregation to ask more complicated analytical queries. In these three queries, you can see that the core component is exactly the join. So what does join query compute? It is essentially the pattern matching problem in the instance hypergraph. The instance hypergraph uses vertex to represent values in the domain of the attribute and use hyperedges to represent the tuples. In the line 3 join, AB join BC join CD, every simple path from A to D is a join result. And in the star join, ABC join AD1 join BD2 join CD3, every star-like subgraph is a result. And in the triangle join, AB join BC join AC, every triangle is a result. So the general join query will find all those subgraphs with specific pattern. This problem in general is NP hard if we take in both the query and the data complexity into account. So in this line of research, we focus on the data complexity and assume that the query has constant size. And our goal is to find the most efficient way to compute the join results. In the last 20 years, the need to process and analyze big data has invigorated this traditional area with a lot of fresh challenges. For example, large volume data cannot be stored and processed by a single machine. People then developed massive parallel systems such as MapReduce and Spark for data processing. Then how to design algorithms that can scale to more than 100 or 1,000 machines while keeping the communication cost low. So we study algorithm for those systems in the massive parallel computational model, noted as MPC model. In the MPC model, there are P servers connected in a complete communication network, and the input data is distributed across the servers. Computation will proceed in sequential rounds. In each round, all the servers exchange message first and then perform some local computation independently. After synchronization, all the servers will enter into the next round. Algorithms in this model are first measured by the number of rounds and then the load, which is defined as the maximum size of message received by any server in any round. As the system synchronization is very expensive, we only consider algorithms running in a constant number of rounds. So the question is, given a join query, a database, and P servers, how to design a constant round algorithm for computing the join results with minimum load? Next, I will show some challenges in designing an MPC join algorithm. Suppose we want to compute the basic two-table join, R1AB join R2BC. Okay, we can simply pick a random hash function which maps the join value to a server ID. Then all the tuples will be sent to the server whose ID matches the hash value. Okay, it works well if all the join values have relatively small degree in both relations. Okay. However, in the worst case, when all tuples have the same join value, all data will be sent to the same server, no matter which hash function is applied to the join attribute. Okay, so in the worst case, the load complexity can be as large as the input size. Then how to deal with the data skew? We first need a primitive to handle this bad case of Cartesian product. The idea is quite cute. We just organize the P servers into a root P times root P grid, okay? For every tuple from the R1, we randomly select a row and send this tuple to all the servers in this row. And symmetrically, for every tuple from R2, we randomly choose a column and send this tuple to all servers in this column. You can easily check that every pair of tuples will meet on some server, and with high probability, every server will receive roughly n over root P tuples. With this primitive, now we are able to handle the data skew in the two-table join. You can view it as MPC version of the sort merge join. Okay, after sorting, okay, all the join values whose tuple fall inside one server can be computed locally, and we are left with the join values whose tuple span over more than one server. And they are at most P-1 such values, and they are potential heavy hitters. Okay, then we need to allocate the servers proportional to their input and output size, and then use the nested loop join to compute their Cartesian products in parallel. And also, this algorithm is already output optimal with the load complexity in this form. Okay, I won't go into the details, but okay, this is a very small example to show how to deal with data skew. When we move to general joins in the MPC model, we will meet the challenges brought by data skew and more complicated join conditions. A common approach in the literature is to investigate the structure property of the pattern, the query hypergraph. For example, the acyclicity or hierarchy or canonical edge covering. Okay, I won't go into the details here, but we have MPC Day on September 27, and I hope on that day I will have time to cover more interesting algorithms for MPC join in the lecture. So next, I want to share with you a big picture of the join algorithm in the MPC model and some interesting difference with the sequential RAN model. The first result is about output optimal algorithm for acyclic joins. So in the literature, more than 40 years ago, the Yanakakis algorithm can already compute all the acyclic join output optimally. However, we observe a separation between R-hierarchical and the non-R-hierarchical join in MPC model. And more importantly, the output optimality for non-R-hierarchical join is quite limited to very small output size. Okay. The second separation is on the worst case optimal algorithm. Okay, in the RAN model, there's a very nice and unified algorithm that can compute all the join results, and the complexity depends on the fractional edge covering number of the join query. And in the MPC model, the worst case optimal algorithm are recently proposed for a cyclic join and several classes of cyclic joins. And we also observe a higher lower bound, okay, for some specific cyclic join. And this complexity, low complexity depends on the fractional edge packing number of the join query. Okay, so you can see the separation here. The third part is on the output optimal algorithm for cyclic joins. And there's a nice Panda algorithm that compute all the join results and whose time complexity depends on the submodular width of the join query, but there's no non-trivial counterpart in MPC model. So there are a lot of interesting questions left in these 3 blocks. The first big question is worst case optimal MPC join algorithm. This is the join I just mentioned. So it has a rather simple structure with AD join BE, join CF, join ABC, join DEF. And it has fractional edge covering number as 2 and the fractional edge packing number as 3. And also the upper bound and lower bounds are already matched. A big question is, what's the worst case optimal algorithm for general joins? And we conjecture that the worst case optimality would be related to the max between fractional edge covering number and edge packing number, but it's still open for both upper bound and lower bounds. The second question is to understand the output optimal algorithm for MPC join. So this line 3 join is the only non-R hierarchical join on which the output optimality is well understood. And this optimality is in terms of piecewise function. So when the output size is small, the classical parallel Yamakashi algorithm is optimal. And when the output size is sufficiently large, the worst case optimal will take over. And when the output size fall in between this region, and our output optimal algorithm is optimal. So the question is, what's the output optimal algorithm for more complicated non-R hierarchical joins? The third question is how to use matrix multiplication to speed up join processing. So in the RAM model, there is a very nice work for listing triangles, use fast matrix multiplication. A natural question is, can we have use the similar techniques to obtain output optimal algorithm for triangle join? We show some lower bound, but we don't know whether this is optimal. And so this question is still open for both upper bounds and lower bounds. A general question is how to use this technique for general joins. Okay, beyond the join, we also want to compute the aggregate function on top of the join results. For example, the sparse matrix multiplication can be represented as a very basic join aggregate query. And we already have some output optimal algorithm for computing sparse matrix multiplication in MPC model. But this is still generally open how to compute other join queries efficiently. Okay, the last question is maybe a big direction is to study the topology of an MPC model. So in the previous one, we talked about the homogeneous MPC such that all the servers communicate with the same bandwidth parameter and the same latency, and they are connected by a complete network. A high-level idea in this model is that we want to take the communication topology into account. And we already have some initial results for set intersection, sorting, and natural join, but I believe there's a lot of work can be done in this interesting model. Okay, thank you.
Questions?
Okay, great.
Thank you.
Thank you.